So we went over this yesterday. So heat is a measurement. Temperature is a measurement of heat, a measurement of the average movement of the molecules in a certain substance. And heat is a measurement of the total energy of motion in those molecules. So heat does depend on the number of molecules present, the speed of those molecules, as well as the type of molecule.
What's the thermal imaging?
I'll show you. So temperature itself is not energy, it's a measurement of energy. Heat is the actual type of energy that temperature measures.
Cool. So, Mr. Buros, the sun gives off energy?
Yes.
Solar power?
All right, so if I show you these, this link works. So if you look at, these are some infrared images. So infrared is a type of energy. It's basically heat energy. And these are infrared images that are measure heat. We go to, sometimes we go to this museum in Ithaca, the Science Museum, and they have a thermal camera. And next to it, they have ice cubes and stuff. And so there's a camera, so you could see your image on the thermal camera. But then if you take and rub your finger like on an ice cube, and you like give yourself a mustache, even though there's nothing there, it cools down the skin in that area. And on the thermal image, you have like a mustache in the camera. So it's kind of cool. That's what these sort of images are. These show, obviously some people. This is a cube that's filled with water, and it shows that there's different colored surfaces, and they emit different amounts of heat. If you look at a building, okay, obviously a building, the areas that are brighter are giving off more heat, and that's because sort of the windows of a building are sort of the least insulated. Okay, same thing here. And they use, you could use these sort of thermal imaging to find people, if people are hiding, they sometimes use thermal imaging to see them. Or if you play video games, sometimes you might see something like that. This shows a radiant flooring. You can have tubes put in the floors. Anyone have floors like this at your house? If you build a new house, you might put radiant heating. Basically, you run these tubes of water that's attached to a heater, and it actually heats up your floor. So when you step on the floor, it's nice and warm, and that heats your house. So here beneath this tile, you could see the tubes from that radiant heating. Okay. Again, you see the different parts of a person. The coolest areas are, the extremities, the ears, and so forth.
Wait, isn't there another person?
What's that?
Can I picture him?
That's a mirror.
Oh, I was going to say, whoa.
Again, you get to see some of these different things. You could see the flow of air through a trombone. You could see this is a squash ball or like a racquetball before playing, and then after playing, sort of could see the change in heat. It's all sorts. You could see the effects of friction on the pavement as you ride your bike over the pavement. This is a warmer area in the pavement caused by the friction of that bike. You can also see the tire.
Is that when you track someone?
That's like skidding, yeah. And so this is the area that was in contact with the ground when they skid. What is this? Different thing. Oh, this shows heating up of oil in a pan. You could see the little convection cells. We'll talk about that today. The components inside a computer. You could see the different heat levels depending on what it is, and so forth. So this is toast. Yep.
I like toast.
This is like wassa bread is like those cracker sort of breads versus a thick piece of bread.
Wait, what's on the next to the...
Okay. And this is just writing on the ground with your finger. Heats it up a little bit, and you can see that when you look with a thermal camera. Yusuf?
Are those like thermal camera apps on phones?
They're not real.
Are they just like a bunch of different colors?
Yeah.
What were they writing?
Oh, and in French? I don't know, something else.
This is a French
Fin? I don't know. I'm not well versed in the Romance languages, I'm sorry.
Very well be a nice guy.
All right, if we show another example.
Ow.
So I have 3 beakers here.
Wait, I don't get it.
Does anybody get it?
I
All right. His name is Beaker.
Oh.
Anyway, he's from the Muppets.
Does he like
So if I have these two glass beakers of water, they're both at 40 degrees Celsius. I have 100 milliliters here. I have 350 milliliters here. Okay. Oh, they're both boiling water. Which one? How do their temperatures compare? If they're both boiling water, actually they're not. Okay. This one's 40 and this one's 40. So they're the same temperature. How does their heat compare? Victoria?
Number 2 is like hotter because it has like the more total amount of heat.
Okay, I wouldn't say hotter, because generally when we say hotter, what are we referring to? Temperature. But you could say it does have more heat. Beaker 2 has much more heat than Beaker 1. So they have the same temperature, but Beaker 2 has more heat.
Yeah,
What's that?
I think that guy's the hottest.
Yeah, I figured.
Just saying.
Oh, yo, okay.
I wasn't even close.
Wow.
Number 2 is more. You don't need to think out loud. It's easier for me.
Shh, Kayla. Okay?
No.
I'm ready whenever you are, Mr. Duros.
Good job, Matt.
I'm ready.
Wait, no, I'm not ready.
Let's go.
No, wait, I'm ready.
1, 2.
Wait, no.
Go.
No, I You win. Oh, yes.
All right, so here, if we have a metal bar, okay? We have a large bar that's 30 degrees Celsius and 2 smaller bars. How does the temperature of all of them compare? Ryan?
The top one is warmer because it has more space to hold the heat.
But I don't want you to say warmer, because warmer is a measure of temperature. What's the temperature of this?
30 degrees.
30 degrees, 30 degrees. They all have the same temperature, but the top bar has
More molecules.
more heat, you could say. And then they have Mr. Arcuri in this bottom picture.
Which one is heat?
So we have a tiny little thimble of water.
Was that tennis?
Yes.
Oh.
And actually, who is this guy in there?
Jiminy Cricket.
There you go, Jiminy Cricket.
At least I know who that guy is.
Yeah. But anyway, it may have a very high temperature. Okay, it's very hot. I see a little steam, and he's happy in there. Or you have this big pool that's cold. Then Mr. Arcuri's shivering there. So even though this one has a much higher temperature, which one do you think would have more heat? This little amount of water versus a whole pool full of cold water. A pool would have greater amount of heat because there's so many more molecules that it overcomes the difference in temperature. Victoria?
I thought Mr. Arcuri was Jiminy Cricket.
Oh, you did? That's not very nice to say, Victoria.
No, but no.
Oh, I can't believe you'd say that about a teacher in our school. That's unacceptable.
Yeah, but you wait.
Are you- All right. Specific heat is a term that we use that's a property of matter. So for any material, you could talk about its specific heat. And it basically is a measurement of how much heat you have to add to that material to increase its temperature. Okay? Water has a pretty high specific heat. It resists changes in temperature pretty well. That's why if you go swimming at night, if you go in a lake at night, it always feels warm because it holds on to the heat from throughout the day, throughout the night. It holds on to the heat pretty well, and so it feels warmer, okay, because it's warmer than the air temperature. At the same time, even sometimes if it's been a cold spring, and then it's a really hot day, but then you go in the pool or you go in a lake, okay, the lake is not warm because it still takes a lot of energy to bring the temperature of that lake up to match the air temperature. So water has a pretty high specific heat. And actually, a calorie, when we talked about calories, we said a calorie is a measurement of what? Of energy. And technically, it's a measurement of heat energy. A calorie is the amount of energy needed. Does anyone know how to finish the Jack?
Boil water.
No. It's the amount of heat needed to raise 1 gram of water 1 degree Celsius.
How much is 1 degree Celsius?
Not much.
So if you put a food with a bunch of calories in a cup of water, would it get really warm?
No, but to scientifically measure the calorie content of food, they actually do that. It's called a bomb calorimeter. For example, if somebody wanted to determine the number of calories in this Tootsie Roll,
Yummy. Give it to Jerome.
what you would do is you would unwrap it,
I don't think it's fair that.
Are you gonna
you
My mouth
would,
is
you
water.
would put it in this device and you would burn this Tootsie Roll. And then in this device you have a thermometer and some water. And basically you measure how much the temperature of the water changes, and that tells you how many calories are in that Tootsie Roll. If this had 100 calories in it, that would be enough to raise 1 gram of water 100 degrees Celsius.
Whoa, wait.
But 1 gram of water is very small. Okay? Or if you have 50 grams of water, it would raise them at 2 degrees Celsius. So as you measure the water, you see that it goes up 2 degrees. That tells you this Tootsie Roll has 100 calories.
What? No.
Sorry.
No.
Wait, my mouth is
I don't
Wait,
get
you have
it.
any more?
Whoa, where did the Tootsie Roll go?
So now my body temperature is going to elevate because I just ate that Tootsie Roll.
Wait,
All right.
do you have any more?
No, I have no more.
You sure? Are you
No.
sure?
He's not
sure. He's got more.
All right.
Caleb sounds psycho.
So
Someone
here's another thing. Can you, coldness is not really a thing. Can you add coldness to something?
No.
Yes.
If you take some water, some water and you put it in the freezer,
Yeah.
does a freezer add coldness to the water?
heat.
Oh.
It removes heat. So heat can move, and heat always moves from a warmer object to a cooler object.
So it diffuses?
Kind of like diffusion. And you can't add coldness to something, you can just take away the heat energy of that object. And that's what a refrigerator or freezer does. So if we have two materials, one that's 50 degrees Celsius, one that's 20, heat from the 50 degrees Celsius object will transmit into the 20 degrees Celsius object. If I combine water, if I have 50 milliliters of water, that's 20 degrees Celsius. And 50 milliliters of water, that's 40 degrees Celsius, and I mix them, I'm going to end up with 100 milliliters of water. What temperature do you think it will be? Kayla? No? David? 30. It'd be 30, right in between, because they're equal amounts of water. David?
Where does the heat go when it's taken away?
What's that?
Where does the heat go when it's
It goes into the refrigerator. Works by, you have a condenser and a compressor in there that basically removes heat. That's why if you ever feel like the back of the refrigerator, what kind of air is coming out?
hot?
Hot. It's like warm air coming out. That heat's removed through those coils on the back.
So it's the heat technically just goes into the air.
Yep.
So if you use a refrigerator as a heater,
Yeah, sometimes it does come out of the heat that from the foods you put in there is what's being removed. All right, now heat can be transferred. We have three main ways that we say heat can be transferred: conduction, convection, and radiation. We're going to talk about each of them. First is conduction. So conduction is, well, let me ask you a question first. If you have a spoon, you're making some soup, and you have a spoon stirring, a metal spoon stirring the soup, and you leave it in a pot of soup that's heating up for a while. Then you go back later and you pick up the spoon.
I know this one.
You know what? You don't know my question.
No, I know the answer.
What type of soup is it?
Chicken noodle.
No, wrong.
Aluminum.
Sorry, Victoria, you're wrong. You did not know the answer.
The cheddar clam chowder.
It was minestrone. All right, anyway, that spoon heats up, but why? Why does the end of the spoon heat up, even though only the tip of the spoon may have actually been in the soup, right?
Because the heat from the soup moves into the spoon, and the spoon holds the heat.
Okay, but what's going on at a molecular level? Matthew?
Diffusion?
It's very similar to diffusion. In fact, if you look up the definition of conduction, often you'll read about it as a type of diffusion, and it kind of is. What's happening to the molecules, David?
Okay, well, one molecule is like really hot and it's like, hey, I'm gonna make you hot. So then this keeps on happening until it gets all the way to the top and it's like, we've made everyone hot.
But how? How does one molecule make the next one hotter? Good on?
Heat conduction until each molecule.
Think about what we said. Heat is the what? What is the definition of heat?
The movement.
Movement of molecules. So as one molecule starts moving faster because it's being heated up, what does it do? Caleb?
It vibrates, so it hits the other and it
Hits another molecule,
goes.
causing that to move faster, which hits another molecule, and so you have this overall heating of the molecules in that substance. Now, here's another question. Why doesn't a wooden spoon heat up like a metal spoon does, Sarah? What's that? It is, that's, the definition is it is an insulator, but does anyone know what the difference is? What's the difference between a metal spoon and a wooden spoon, that a metal spoon heats up but a wooden spoon doesn't? Lisa?
Molecules are further spaced, so
Not so much that they're further spaced, Matthew.
That's what's like density kind
Not quite density. It's also, what else does metal do that wood does not? Another factor, in fact, uses the same word. Matthew?
Conducts electricity.
It also conducts electricity. Why do metals conduct electricity but not plastic or wood? Think about metals in the periodic table. What do we know about their valence electrons, Victoria?
That they're under 4.
They're under 4. They have low number of valence electrons. They have extra electrons in that outer shell. Those extra electrons are more likely to move out and knock into other. So that's why they conduct electricity. It's also why metals conduct heat better. When molecules bump into each other, those electrons and those atoms knock into each other, causing them to accelerate.
I have an example and a good way to remember. So metal, it's kind of like, the soup is kind of like kids on a sugar rush. And then the metal is kind of like little kids. So it'd be like, hey, want some sugar? And then the little kid in the metal will be like, sure. And then he'll get on a sugar rush.
Okay.
But then the wooden spoon is like an adult. It's like, want some sugar? And they're like, no. I am watching my cholesterol.
All right. There's no cholesterol in sugar, but okay, interesting analogy. So anyway, conduction, generally we talk about conduction in solids. We have other methods of heat transfer that we'll talk about in liquids and gases. And good conductors are metals, and poor conductors are non-metals, things like wood, plastic, rubber. Yes. If you have a plastic sort of part of your chair that you're sitting on and a metal part. If you touch both of them, so how is their temperature compared? You think so, Jack?
They're the same.
They're the same temperature.
Really?
They both have been in this room all day long. They're both at room temperature.
Mine feels a lot colder.
But when you put your hands on them, they don't feel the same. Okay? Which feels colder, Nicholas?
The metal.
The metal feels colder. So the question is, why?
Because it has like it can conduct heat, so that it will have the
He can be able to just take away.
Wait, I have an
As you touch the metal, it conducts heat away from your. Because what's warmer, your hand or the chair?
The chair. Your hands.
Your hand. So as you touch the chair, as we just talked about, heat will move from a warmer object to a cooler object. So heat will transfer from your hand into the surface. In touching the plastic, because it's an insulator, very little heat leaves your hand. But when you touch the metal, it's a better conductor of heat, and more heat energy will leave your hand, and thus it feels colder.
That makes sense.
So which is colder? Neither. They have equal temperature, but the metal feels colder because it's a conductor, and the plastic is the insulator.
What are they listening to?
Classical music.
Michaela?
So like when you touch an ice cube,
Yes.
I don't know what I'm
It conducts heat away from your skin, making your hands
Oh
feel
yeah, no,
cold.
okay, yeah, so that, okay, so like when you touch ice cubes, that my hand goes cold after?
Yep. So in conduction, the molecules are not moving. So it's not like a molecule in a metal spoon gets heated up and then moves to the end that you're touching. It's that the molecules vibrate faster, bump into each other more, and that continues. Heat's going from, in this case, this is a metal rod. The heat would be transferred from the candle down to this person's fingers because the molecules would bump into each other. Got this picture of Mr. Arcuri and his wife. And so this is why, you know, Mr. Arcuri's wife, she's pretty smart. She used a wood stick to toast marshmallows. But when they were camping last year, Mr. Arcuri used a metal rod, and you see what happened.
He burned a hand.
What's that? Who's floating?
No, the stick.
Because it's hot and he dropped it. This picture, this photograph was taken in the split second when his hand was burned and he
Yeah,
let
no, but you
go.
said this right. There's a cloud at the bottom.
There's a what?
Cloud. Cloud.
He's
No,
looking
that's
at
the
the
dirt.
air. Another.
Yes,
Why
Liv?
is he wearing a pink dress?
Oh, I don't know. I think those were his pajamas. That's what they were. David?
Okay, I was gonna. Michaela, you made me lose my train of thought.
You told me that in the last picture, Mr.
I really
Claus
do.
was holding a brown stick, and his wife was holding a gray stick.
No, this is bread. This is a red hot metal marshmallow puff.
Is Mr. Here wearing high heels?
Yes.
It's okay.
Would you mind keeping the slide on the projector so I can go get Mr. Arcuri?
Why? He's seen this photograph of himself.
No,
before.
we need to remind him of his camping trip.
All right, number 2, we need to get through these 3 methods. Convection. Convection is another means of transferring heat. We usually talk about it in solids, in gases and in lipids. And in convection, the molecules actually move from place to place. So in conduction, the molecules are basically staying where they are, bumping into each other, causing other molecules to vibrate faster. But in convection, you have molecules actually moving. We call this movement of molecules a convection current. So, if we think about this container of water being heated by a flame here. So which water would heat up first?
This side.
Yeah, this side right here. If you think back, when you heat up a material, what happens to its density?
Changes.
How does it change?
It gets higher, lower. As inflated.
Density decreases because it expands. So if the density of this water decreases, what happens to it? It rises.
Oh, I see now. Oh, I see where he rises.
And then new water comes in sort of to take its place. And this is what we call a convection current. When you boil water, okay, those bubbles coming up from the water because that water that's heated down to the bottom of the pot rises up and creates this convection current. At your house, you may have a convection oven,
Yes.
which the air is rotated and moves around your oven, cooking foods faster. Andrew?
This is also how continental drift works with the lava.
Oh, through the movement of magma within the earth?
Yes.
Yes. Michaela?
How does new water come in?
It's just because as water moves up, it just sort of, as it moves, it sucks the water in with it. And new, cooler water moves into that area, heats up, and you have this sort of
So does
cycle.
that hot water go back into like?
Yep, and it sort of loops around, because when it gets to the surface, it cools down, and then it comes back around.
Oh.
So that's what's being shown here. You heat up this water with this Bunsen burner, and you have this cycle, this convection current. Same thing, a heater in the room works as it heats up air. The warm air in the room rises, and then cooler air takes its place, heats up, and that's how you heat the entire room.
Same exact heater.
It's also why sometimes a ceiling fan is often used in people's houses, because as warm air rises to the top, you can, in a big house with high ceilings, you could force that air back down to the floor again. David?
So going back to the thing we did before
Conduction.
I always forgot.
Conduction.
Conduction. If you were to hold that metal part for an extended amount of time, would the metal and your hand become the same temperature?
Eventually, but it would burn your skin first, yeah. And then the last type of heat transfer is radiation. Radiation is a means of heat transfer through empty space. It doesn't require molecules to vibrate or molecules to move from place to place. It doesn't require any molecules. Okay? It's how the sun's energy reaches us. Energy from the sun cannot reach us through conduction or convection. Why not? Why can't the sun's energy reach us through conduction or convection? Nicholas?
It's too far away.
Not so much the distance,
There's empty spaces.
because there's empty space. Space is a vacuum. And there are no molecules to bump into each other for convection. There's also no molecules that can move from the sun to the earth to spread heat through convection. Instead, that heat reaches us by radiation. If you have a fire or something, put your hand up near it. That heat you feel coming off of the fire, you feel that because of radiation. Okay? It's not the molecules close to the fire are then coming to your hand. It's that heat energy is radiating from that fire. Now there is some convection because the air above it heats and that air rises, but the heat you feel, the immediate heat from that object, is radiation. Okay? So feeling a heat of a fire is radiation.
Why is there like a green aqua?
So, one more slide here. This will be our last one for today. In this example, this person holding the pot over the fire, all three methods of heat transfer are being shown. Which method of heat transfer is this one indicating? Matthew?
Convection.
Convection. How about this one, Michaela?
Conduction.
Conduction. And this one, Vedant? Radiation.
How is like the chemistry without using anything to do with something radioactive?
Well, certain types of radioactive particles move through the process of radiation. All electromagnetic radiation moves using the same principles.